All right, so before we begin today's lecture, let's go back to college algebra and I won't say redefine, but just view a concept that we've seen before, but probably have forgotten. Okay, so we know that if we have let's see, can I if we have we know that if we have this function, all right, it's a quadratic function, and we use quadratic functions quite often in the previous courses, college algebra, intro to college algebra, because we can do so much with them in terms of trying to solve problems. All right. Well, in this particular case, you would look at it, you'd be like, okay, so I can't factor it, so I'll use the quadratic equation. Okay. And so that's how we solved quadratic functions. Well, what if we had problems that look something like this? Something like this. Okay. Well, you have had problems similar to this, and you would say, okay, well, um, you don't want to FOIL this, combine like terms, all that stuff. So what you would do is you would make a substitution. Okay, and the substitution we would use back then was u, and so we would say, okay, so we're going to let u equal to x minus 3. Okay, and by letting u equal to x minus 3, we now have the equation that looks like this: u squared plus u minus 9 is equal to 0. Okay, and let's actually make it a little more complicated. Let's put a let's put a 3 here, a 3 there. All right, and so let's go ahead and also fix this up. All right, all I'm doing is just making it a little more complicated. So 3u minus 9 is equal to 0. Okay, so what we did was we changed our original equation by saying, okay, we're going to let u equal to what's inside these parentheses. And by letting u equal to what's inside the parentheses, right, that's the substitution here, I was able to now change it to u squared plus 3u, and of course the minus 9 stays the same. And then from here, we're able to solve this equation for u, and then we'd substitute back our original substitution. All right, this was how we solved quadratic equations by substitution. So we're going to be using a similar concept today with integrals. Right, so we've got, well, that's the title. Let's put 4.5 there. So 4.5, integration techniques, substitution. So this is where it gets a little sticky, a little dicey with this class. And, well, hopefully by this section, we will fully understand how to do this. All right. So this is just a kind of recall our integration rules here. This shouldn't be anything new to you. But up until now, we have had problems that looked like, and let's just go ahead and we'll just go ahead and snip it. Okay, we actually have not had problems that look like this, but we have had problems that have a dx here at the end. Okay, and up until now, we haven't really even messed with it, and that's okay. In a normal calculus sequence, we would have done some things called implicit differentiation, and you would be a lot more familiar with that dx. Well, today we're going to actually deal with that dx, and we're going to integrate problems that look like example 2. So example 2, that looks like an absolute mess of a problem, and to be honest with you, it kind of is, right? But what we're going to do is we're going to do that substitution that we did on the very first page, kind of like how we would do substitution with our quadratic equations. So what we're going to do here, all right, we're going to look at this problem and we're going to say, okay, so we're going to kind of try to reverse the chain rule. Okay, so if you recall the chain rule, you know, we took the derivative of the, or let's see, we took the exponent out, oh, that's not what I wanted. I'm trying to circle this. We took the exponent out here, put it out front, differentiate the inside, and put it in the back. Okay, we're kind of doing the opposite of the chain rule. So what we're going to do is we're going to make a substitution. So let's go ahead and write this real quick. We've got the integral of 3x squared times x cubed. I might be making that a little too large. Well, okay. So looking at this problem, what seems to be the most complicated part, right? What seems to be the inside part of the chain, right? So what we're going to do is we're going to make the substitution. We're going to let u equal to what's inside our parentheses here. Okay, so we're going to say u is equal to x cubed plus 1. Okay, so by letting u equal to x cubed plus 1, right, we now have the integral 3x squared, and then we have u raised to the 10th power dx. Okay, well at this point we're kind of stuck because, well, now if you recall, you know, when you go to solve problems, let's put a new page here. If we had a problem that was like I don't know, y is equal to, no, okay, here's a good one. In the past, we have done something like this. If we had some sort of box, and we would say that the length of a box is two times longer than the width. Okay, so it'd say this is the width and this is the length. Well, we would if we were to find the area of this box, we would say w squared plus L squared. Okay, and again, let's just say the area is 99. Right? So we would have this equation. Well, this equation isn't possible to solve as of now, right? Because we have two different variables. We have a length and a width. In order to solve an equation, one equation, we have to have one variable. We can solve a two-variable equation if we have two. We can solve a two-variable problem if we have two equations, three-variable problem if we have three equations, and so on. But since we only have one equation, we have to have one variable. So, you know, in our problems, we might have heard something like the length is 2 times the width. Okay, well, that's cool. So what we would do here is we would say, okay, so the length is going to be 2 times the width. Okay, so that means that I can change this L squared into 2w squared. Now it becomes a problem that we can solve because we have only one variable. All right, so with that concept in mind, going back to this problem, notice that we have two variables, an x and a u, as well as dx, right, with the derivative of x. So what we have to do is we have to change this entire problem down here into variables with u's. Well, how do we do that? Well, we're going to do u sub. So what we're going to do is we're going to look here at this problem, and we're going to take the derivative of u. So what is the derivative? What is derivative of the left side? Well, derivative of u is du. What's the derivative of the right side here? Well, x cubed. The derivative of x cubed is 3x squared, and then of course plus 1. Well, that doesn't have a derivative, and then we say dx. Okay. So now that I look at my new equation down here, what needs to change and so I can get all u's? Well, we have a 3x squared here and we have a dx. Okay, well, if we look at the substitution up here, well, it just so happens that du is equal to 3x squared dx. which is exactly what I'm wanting to take out. Okay, so I'm wanting to take out stuff down here. Let's take those arrows away. I want to take these out, and I'm going to put du in. Okay, I'm just making a substitution. So my problem now becomes the integral. All right, and then we'll do, try to keep this color coordinated here. U raised to the 10th power, and then du. Okay. Again, because this du is equal to 3x squared dx, well, that's exactly what I'm going to take out of my problem and substitute in du, which you see here. Okay. Now again, if this doesn't fall on you right now, if it's not clear now, there's plenty of problems in this section. Okay. So anyways, at this point, now this particular integral is so much easier to solve, right? And again, we're going back to here. This quadratic equation is so much easier to solve than this one because we made that substitution. Okay. Well, what is the integral of u raised to the 10th power du? Well, let's put an arrow down here. Okay. Well, that means we we raise the exponent. It goes up one, so we're going to have u to the 11th and then divide by the new exponent. So u to the 11th plus c. And let's actually put that in green to just really kind of show the very end here. U to 11 over 11 plus c. Okay, so we made the substitution, and it became super easy to solve. Right, but we're not done yet. All right, why are we not done yet? Well, because my original equation didn't have a u in it, did it? Right, my original equation had x's. Well, what we're going to have to do here is resubstitute back in what we said was for u. And honestly, that's all right. For consistency's sake, let's actually do use that in white because we're not done. Okay. Now we'll be done. So what did we say that u was? Well, we said that u was x cubed plus 1. So we're going to say x cubed plus 1 raised to the 11th, plus 1 raised to the 11th power over 11 plus c. Okay, and now we are done. And hopefully this toolbar down here is, at least for those in the lecture, not in the way. Right. So that's our first u sub integral. Let's move on and do another one. Just kind of get super familiar with this process. All right, so I'm going to go ahead and rewrite this integral. I'm not too much of a fan of putting the dx in line with our fraction. So let's 1 plus. Okay, now that's too small, Sherman. Sorry, like I said before, the pen doesn't pick up if I make small movements. All right, so 2x, and then we'll have dx out here. Okay. So we've got the integral of 2x over the quantity of 1 plus x squared dx. All right, so this is my problem. So looking at this, what is the most complicated part of this function? Okay, well, it looks like it would be the denominator. All right, so what we're going to do is same thing. We're going to make the u sub. How to put the down? So we're going to let u be equal to this denominator, 1 plus x squared, okay? And it's also, you'll also kind of have an idea of it because we know we can see that we have x squared down here. What's the derivative of x squared? Well, that's 2x, okay? And that's going to come in handy when we do this. All right, so if I'm going to take the derivative of both sides, what's the derivative of u? Well, that's going to be the derivative of u. And that's going to be equal to, what's the derivative of 1? Well, that's going to be 0 plus 2x. So it's going to be just, or I'm sorry, plus x squared. The derivative of x squared is 2x. Okay. So, and then of course dx. So I'm going to make this substitution here. So I'm going to have the integral of 2x over u, because again, I let the denominator be equal to u. Excuse me. Keep looking back because I want to maintain the way I write this. So looking at this, after I made my u sub, what do I see here that I need to take out? That has the variable x in it. Well, I have a 2x and I have a dx. So I need to make that substitution. Well, it just so happens that du happens to be equal to 2x dx. Okay, so same as before, it just so happens that all I have to do here now is I can now write this as 1 over u. I'll put u here. And then du. The derivative of u. Okay. Because again, my 2x dx, that's what this is, 2x dx. So I can just replace 2x dx with du. And now I have a nice handy dandy integral with just u's. Okay, so what is the integral of 1 over u? Well, that's just going to be the natural log of u. So we're going to have the natural log of u plus c. All right, well, again, we didn't start off with u's, right? We started off with x's. So we're going to make that substitution back in. 1 plus x squared is going to come back in for u. So we're going to have the natural log of 1 plus x squared plus c. Okay. So hopefully I can remember the format I used so I don't have to flip back and forth. Okay, so this one looks pretty similar. Right, pretty similar, but we're getting a little more complicated. Let's go back and look at the previous problem. We didn't really have the entire binomial on the bottom raised to a power, so it doesn't go away. All right, so we had, in this particular problem, we had 1 plus x squared. So our new problem, we're going to have the binomial 1 plus x squared, but it's going to be raised to the 5th power. But it's going to be along the same lines. So again, let's go ahead and rewrite this. And I just, again, I just kind of like to put the dx all by itself. I don't like to put it in line. It's just notation that I've been used to, but it really doesn't make that big of a difference. So anyways, looking at this particular problem, it should be abundantly clear what my u should be. All right, my u is going to be what's inside the parentheses there. It's supposed to be 1 plus x squared. So let's rewrite this problem. So I'm going to have a u, let's put this in, it's 2x, and then my denominator is going to be a u raised to the 5th power dx. So again, we're hopefully we're starting to see a pattern. We're starting to be like, okay, we get it now. Let's fix this a little bit. So looking here, we've got a 2x and dx. Well, we have to change those to u's or with respect to u's. So what we're going to do is we're going to say, well, we're going to take the derivative of both sides here. So the derivative of u is du, the derivative of 1 plus x squared, is going to be equal to 2x dx. And again, 2x dx, well, that just seems to be uh, the, the perfect problem. So we're going to change this into the integral of 1 over u to the fifth, and then du. Let's see, did I? Yeah. Again, let's just keep consistent with the colorizing here. Alrighty, so if we were to integrate this particular problem, we know that we're going to start, we can, let's go ahead and actually rewrite this as the integral of, because we're going to put this in the numerator, it's going to be u to the negative 5, right? We're just getting rid of the fraction, du. That makes it easier to go up 1. So if I'm starting at negative 5 and I go up 1, my problem becomes u to the negative 4, then we divide by that, over negative 4 plus c. And again, we didn't start with u, so we're going to make that substitution back in. 1 plus x squared. So we're going to have a, well, yeah, we'll just go ahead and keep it in the numerator for right now. We're going to have a 1 plus x squared raised to the negative 4 power over negative 4. And, I really don't want to do this on the next page. Let's see if I can slim this arrow down a little bit. All right, so we know that the negative exponent goes into the denominator. This negative 4, the negative in front of the 4, can go out front in front of the entire fraction. So we're going to have a negative 4 times 1 plus x squared raised to the 4th power, and all of that under 1, and plus c. Oh, plus c. All right, let me move it back over to the right or left again. Actually, let's just write it smaller. And plus c. There we go. Okay. So these first three, they've kind of been the same. There are some variations here, and I don't exactly remember when we see them. But for the most part, the variations are going to be pretty small. You're going to know generally what to do, what you want, what you need to substitute, and how you move things around. And what I mean by how you move things around, hopefully we'll get there. One of the things that are easier done than said. All right, so let's go ahead and rewrite this problem. So we're going to have the natural log of 3x all over x, and then dx. Okay, and of course it has the rule that x has to be greater than 0, and let's just go ahead and put that there just for continuity's sake there. All right, so looking here, what should my u sub be? What should my u be here? Well, the natural log of 3x, that is an actual number. All right, the natural log of 3x, that's an actual number. I can't just say let's let u equal to 3x. Okay, because the natural log of 3x is going to be some number. So instead, what I'm going to have to do here, again, looking at this, we're doing the kind of the reverse of the chain rule. Between the numerator and the denominator, which one seems like it'd be the most complicated, right? Well, it looks like the natural log of 3x would. So we're going to say, we're going to let u be equal to the natural log of 3x. So if I do that, if I make that substitution, I'm going to have the integral of u over x dx. Okay. Well, oh yeah, let's change the colors. Keep forgetting. U over x dx. Okay. Well, um, I've got a dx here and a u here. Doesn't really help too much. Okay. So what needs to happen here is I need to replace that that x and dx. Well, let's go up here. We're going to take the derivative of both sides again. So the derivative of u is going to be du, and then the derivative of the natural log of 3x. Well, that's going to be, and let's actually do this down here because I feel like it kind of could get lost. If you recall, the derivative of the natural log of 3x is going to be 1 over what the argument is. The derivative of the argument is supposed to be 1 over 3, and that's going to be times the derivative. So that's going to be 1/3 times 3. Okay. Well, 1/3 1 over 3x. Sorry. So that would be the natural log. Let's start that over. I don't feel like I explained that well. Just to recap, the derivative of the natural log of x is going to be 1 over what the argument is, x. All right. Not the derivative of it. 1 over x. And then, of course, if we have a 3x here, we have to use our chain rule. So if we said natural log of 3x, well, that's going to be equal to 1 over the argument, 3x, times the derivative of the argument, which is 3. So it becomes 3 over 3x, or in other words, well, it just so happens that's 1 over x. So the derivative of the natural log of 3x is going to just simply be 1 over x. So we've got, where am I looking? It's equal to 1 over x dx. Okay. All right, and again, well, it just so happens that I'm wanting to replace what appears to be a 1 over x, right? This is 1 over x, and then of course the dx. So there's not much I have to do here. All I have to do is say, okay, well, I'm replacing the 1 over x dx with a du, so it's just going to be equal to the integral of u du. Okay, and then from here, it should be pretty easy, right? Well, what is the integral of u du? Well, that's just going to be u squared over 2 plus c, which we know is going to be, we said that u is natural log of 3x, so it's going to be the natural log of 3x squared over 2 plus c. Okay. And moving right along. All right, so we're getting into things that look a little more complicated. But like I said, we just make our u sub, and it makes it so much easier. See how like my pen likes writing these small ones. That's not bad. Okay, good. I think I might have lucked out there though. All right, so we have the integral of x times e raised to the x squared. All right, now I do remember this problem. This problem is going to be one of those where it's not abundantly clear how we do the u sub. Up until now, we just substituted in basically what du is equal to. This time we're going to move things around a little bit. So let's looking at this, what seems to be the most complicated here? Well, I wouldn't say I kind of misspoke, but I might have messed up earlier saying that the natural log of 3x is a number, so we're not gonna take the u of 3x. But in this particular case, we are going to take we're going to let u be equal to my exponent of my exponent of e. Okay, because again, we're doing the reverse of the chain rule, so we're essentially just looking for the No, I guess that does fall in line with what I was saying. All right, so what we are going to do is we're going to say u is equal to x squared. Okay, so we're only focusing on this up here because we do the reverse of the chain rule, and again, is its own number. It's 2.71, right? So if I were to rewrite this now, I would have the integral of x and then e raised to the u power dx. Okay. Well, same procedure as before. I have an x and I have a dx that I need to get rid of. Okay, so let's go up here and let's take the derivative of u here. So we're going to have du, and that's going to be equal to, it's going to be equal to 2x dx. Okay, and so we have run into our first problem that is different from before. So now we can't just make a very convenient substitution. Okay, up until now, this du, well, oh no, I didn't mean to circle it. Well, I gotta erase that circle, guys. Hang on. So when I change pages, it basically saves what I just drew, and I can't hit the back button. Right, there we go. All right, so up until now, the du has basically just been the one being plugged in. I haven't had to do any other changing around. I haven't had to do any more substitution up until this point. However, now I can't just simply substitute in du in for this because, again, as we said, we have an x and we have a dx. So we need to figure out how to substitute in for x dx. So what we need to do here is we need to look at this particular equation, and we need to have an x dx on one side. Okay, if I'm trying to replace x dx, then I'm also going to have an x dx on one side here. So that should be a pretty easy task, right? Because I just need to isolate this. So therefore, I'm just going to divide both sides by 2. So now I'm going to have a du over 2, and that's going to be equal to x dx. Okay. And again, let's go ahead and go back and recap because I feel like this is a kind of a tricky part here. All right, so this is one we started with. On this right side here, the 3x squared dx, that happens to be what I'm replacing here, 3x squared dx. So all I had to do is plug in a du and be done with it. All right, and that was the case for every single problem so far. Had a 2x dx, well, 2x dx, so I just replaced them with a du. 2x dx, 2x dx, and kept on replacing, and so forth. And again, this problem now, if I were to just stop at this stage right here, the 2x dx, it doesn't have a home in this integral because I don't see a 2 anywhere. What I do see is an x dx. So that's why that's why I had to do one more step here, and I had to put an x dx off by its side in this equation. So in doing so, now I can make that proper substitution. The proper substitution now is going to be I'm going to put in a du over 2 in for x dx. So my problem now is going to become the integral of e to the u power, and it's going to be, I'm substituting in a du over 2, and let's fix that up a little bit, times du over 2. And again, the du over 2 just replaces the x dx. And if it helps, let's actually rewrite this just to make it a little bit easier. We have e to the u and then x dx. Okay, so just to make it a little bit easier, this x dx is being replaced by du over 2 because that's the substitution we made right here. X dx is being replaced by du over 2. Okay. All right, well, if we were to fix this up, and again, like as I've mentioned before, I don't really like the d's in line, so let's go ahead and change this now into the integral. All right, I'm just basically rewriting this now. E to the u over 2, and let's make that blue, over 2 du. Okay, and again, all I did is just put them nice and neatly, and I put the du off to the side. All right, well, we know that from our integration techniques that, well, this is essentially a 1 over 2, right? 1/2. So I can pull that out in front. So my integral now becomes 1/2 and then e raised to the u power du. Okay, so hopefully you did this. I haven't lost you. And again, and I'll say again. And now at this point, we can begin the process of integrating. Um, and so this becomes 1/2. Yeah, 1/2. All right, what is the integral of e to the u? Lucky for us, it is e to the u plus c. And then, well, we didn't start with a u to begin with, so we're going to have 1/2 e to the, my u was x squared, so e to the x squared plus 2. Not plus 2, plus c. Okay. Alrighty. So in this particular case, we had to do one more step when we took the derivative of u, and that one more step was to get exactly on one side what we have remaining in our integral that I need to substitute out. Okay, so we're gonna have us at a natural log problem. So again, I'm gonna rewrite this as 6x plus 1 over that, and then dx. And again, just like to rewrite things that make it that I'm used to rather. So x is not equal to 1 negative 1/6. And again, this has, I mean, it has something to do with the problem. It's just a formality. It's just a rigorous definition saying, okay, so we know that x cannot be equal to negative 1/6. Otherwise, this entire problem just is dead on arrival, right? Because it's undefined. Anyways, the u in this particular case should be pretty darn easy. There's no other option. U is going to be equal to 6x plus 1. So if I were to rewrite my integral here, it would be 1 over u, and then I have dx here. Okay, so in this particular case, what do I need to replace? Well, I've only got one thing to replace here, and that is a dx. Okay, so let's go ahead and rearrange this particular equation. Okay, I take the derivative of both sides, so I've got du is going to be equal to a 6 dx. Okay, well, same as before, same as example 6, I have a dx, but up here I've got a 6 dx. Well, I need to replace this dx with this dx. So all I have to do is isolate this dx. So by isolating the dx, I'm going to divide both sides by 6. So I'm going to have a du divided by 6, and that's going to be equal to dx. So that substitution now looks like this. So I can say the integral of, now I'm replacing that dx, so it's going to be 1 over u, and I'm replacing this dx with this dx, which is du over 6. So it's going to be times du over 6. And I don't really like it written like that. I like to have, again, the du out by itself. So I know d over 6 is just going to be 1 over 6 du. Okay, so 1 over 6 du is the same thing as du over 6. And since this 1/6 is a constant, I know I can change that now. I can pull that out in front of the integral. It'll be 1/6 times the integral of 1 over u du. Well, what is the integral of 1 over u? That's just going to be a natural log of it, right? We're going to take the natural log of it. So we're going to end up with 1/6 the natural log of u, the absolute value of it rather, plus c. And then again, we didn't start with a u, so we have to just change that u back. So we've got 1/6 the natural log of 6x plus 1 plus c. Okay, so just substituting u's in. So this is slightly more complicated than what we're used to, but I do feel like you guys are in this class for a reason, so you'll get it. Example 8. All right, so now we're going to be doing a definite integral. Right? Definite meaning we have actual points on the integral that I need to calculate. All right, so this is the integral from 0 to 1 of 5x times the quantity of square root of x squared plus 3. So let's go ahead and rewrite this. Actually, I don't necessarily need to. It's written pretty nicely, but I guess to keep in line with everything I've done so far today. You know what? Let us actually rewrite this to x squared plus 3 raised to the 1/2, right? Because we know that the square root of something is actually raised to the 1/2 power. Okay. All right. So the u sub here again should be pretty obvious. It's going to be what is inside the parentheses there. So it's going to be u is going to be equal to x squared plus 3. Let's rewrite this integral now. From 0 to 1, we got 5x. Okay, so obviously looking at this problem now, we have some problems because we have the 5x here, and then of course we have the u in here. Right, so we look like we're going to run into a little bit of a problem. dx. Okay, so what is that problem we're running into? Well, again, looking at this problem, I still have an x here, and I have a dx here. But I also have a 5 here. Okay, and that 5 could potentially be a problem. But we have to remember our integral rules, right? We actually can put that 5 on the outside of the integral because it's a constant. So I can take this 5, put it on the outside of the integral, and we can rewrite this now as a 5 times the integral from 0 to 1. Okay? So now, disaster averted, right? But we still have to deal with this x dx. So coming up here, let's go ahead and take the derivative of both sides. We have the derivative of u is du. That's going to be equal to 2x dx. And now, similar to how the first few examples, we really drove the point home. All we had to do was substitute in du. Now we're really driving the point home that, okay, so we're going to do a little bit of rearranging. We have x dx that I need to replace. So I'm going to have to isolate this x dx. Well, same as before, I'm going to divide both sides by 2. So I'm going to have a du divided by 2 is equal to x dx. And I meant to erase those red lines here. There we go. All right, so now I can rewrite this problem as we got 5 on the integral of 0 to 1, and replacing the x dx with du over 2. And I'm just going to go ahead and instead of writing du over 2 and splitting up, I'm just going to go ahead and write this as 1/2, okay? Or I'm going to rewrite this as nice and neat. So I've got u raised to the 1/2 power. All right, it's going to be times 1/2 du. Okay, and again, I just took this du and I went ahead and kind of split it up already into 1/2 times du. Well, we have this 1/2, we have a constant here, and I know I can take the constant and put it out in front. So 5 times 1/2 is going to be 5 halves. So this particular problem now becomes I don't need an arrow there. Now it becomes 5 over 2. Again, that's 5 times 1/2 because I'm taking this 1/2 putting it out front. Uh, the integral from 0 to 1 of u on the 1/2 du. So yeah, we're going to write that. I think actually we're gonna have to do this on the next page as well because that's a definite integral. So I'm not gonna worry too much about scrunching this up. Okay. All right. So this becomes our problem, and let's go ahead and actually put this into a definite integral. So we've got a 5/2. Yeah, we can do that. All right, so 5/2, and then we've got 2/3 times u to the 1/2. No, times u to the 3/2, and then plus c. Okay, so let me make sure. We go up 1/2 divided by 3/2. Yeah, okay, good. All right, so this now becomes my essentially my indefinite integral, right? But this is a definite integral. Definite meaning we were going to actually evaluate it at some points. So let's go ahead and snip this and put it on the next page. I guess we're going to snip all this just so I can remember. Okay. So what we're going to do is we're going to take our integral and we're going to evaluate it from 0 to 1. So we're going to say, all right, so we're going to say 5/2 times. Oh, I didn't finish it. Sorry. All right, so I noticed I didn't finish it because we still have a u. Okay, so our original was x squared plus 3 was equal to u. So let's actually finish this off now. And we'll stay consistent with the previous examples. So we're going to say 5/2 times 2. Oh, that's easy. Okay, so 5/2 times 2/3. Sorry about that. Getting a little ahead of myself. I know that 5/2 times 2/3 u to the 3/2. Well, this 5/2 and 2/3 they're gonna multiply by one another. The 2's cancel, so I'm gonna end up with a 5/3. Okay, so this becomes a 5/3, and then my u was x squared plus 3, so x squared plus 3 raised to the 3/2 plus c. Okay, now let's work on uh, the definite integral. So we know that's essentially going to be, and I'm going to go ahead and keep that up there and just basically rewrite this so I can uh, really show on the notes what we're doing here. X squared plus 3 raised to the 3/2. All right, and we're not going to put plus c because we are going to actually evaluate this integral from 0 to 1. Now we can do a little snipping here. Put on a new page. Right. Well, evaluating it at 0, well, that's not necessary. Well, it is necessary. Okay, never mind. Okay, so let's actually do this. If we plug in a 1, where's my calculator? Right. So if I were to evaluate this, I will have I'm going to end up with basically say 5/3, and that's going to be times um, uh, 1 squared is 1, 4 raised to 3/2, so it's going to be 4 raised to 3/2 minus, and if I plug in a 0 there, it's just going to be 3, so it's going to be 3 raised to 3/2, so 3 raised to the 3/2 from, well, not from, but that's it, and so this becomes 5/3 times 4 to the 3 halves. So 4.67. And I mean, realistically, the last part of this particular problem we've done before with definite integrals. The new steps involved here is just going to basically be the u substitution here. Okay, but we did obviously solve this definite integral. All right, so the last example is going to be another one of those where you're going to have to make a substitution and you're going to have to kind of just think about it. Okay, so let's go ahead and solve this problem like we have been solving, and we'll see where the issue comes up. So let's go ahead and don't think I have to rewrite this, but let's go ahead and rewrite this. X plus 2. Okay, so my u is going to be x plus 2. So if I rewrite this, well, I'm going to have x over u dx. Okay, so it looks like what I need to replace here is an x dx. All right, well, so far so good. Let's go ahead and differentiate here. So we're going to have the derivative of u is du, and then the derivative of x plus 2, well, that's just going to be, it's just going to be dx. Okay, so we're trying to replace x and dx, but all we have here is a dx. So we're going to have to get a little clever here, and let's go ahead and rewrite this like we have been doing. So we're going to have an x over u, and like I said, I'm replacing this dx with a du. All right. Well, again, that we have the problem that my x is still there. How do I deal with that x? Well, we're going to have to be clever, like I said, and look at this problem, or look at this equation rather. If we said that u is equal to x plus 2, okay, then that must also mean if I solved for x, then that x is going to be equal to, I subtract 2 from both sides, x is going to be equal to u, oh man, pen's doing some crazy stuff here, u minus 2. So there's my substitution for x. My substitution for x is going to be u minus 2. So I can rewrite this even more as u minus 2 over u du. Okay. And now at this point, the problem I'm going to say should be pretty clear, but u minus 2 over u, well, I can pretty much, I can fix that up as u over u minus 2 over u, right? By splitting up this fraction. And then, of course, du. So that would become, well, u over u, well, that's just going to be 1. So 1 minus 2 over u du. Okay, so let's go ahead and put this on the next page. So we have the integral of 1 minus 2 over u du. Well, if we were to integrate this, all right, well, what is the integral of 1? Well, I mean, we have, what is the integral of 1 with respect to u? Well, that's just going to be u. And then the integral of 2 over u, that's just going to be, so minus 2 natural log of u, and then plus c. Okay, well, we're not done because we said that u is equal to x plus 2. So let's go ahead and put x plus 2 in here. So we're going to have x plus 2 minus 2 natural log of x plus 2 plus c. All right. Well, at this point, we're not done yet because what up until this point, what is our C meant? Okay, our C is meant plus some constant, right? Because we know that the if the constant can be anything, um, but it's going to be some number, right? So since it is some number, it doesn't matter what number. I mean, it could be 13, it could be 15. It doesn't matter what number we have. So what we're going to do here is we're going to combine like terms. So you might be looking at this problem and you might be thinking, okay, well, cool. What are my like terms? Well, in calculus, again, if we took the, let's see, let's actually go back to when we first started doing integrals. Okay, if we said what is the so if we had 2x plus 3 and 2x minus 3. Okay, so these threes are obviously different, obviously. Okay, well, if I took the derivative of of these two equations, the derivative of both of them is going to be 2, right? So it's going to be 2. Well, if I integrate 2 with respect to x, I end up with simply a 2x. And then, if you recall, that's why we put the plus c. Okay, because we're trying to say, okay, well, when we integrate this function, the c can be anything. And here we see that the c can indeed be anything. Okay, but it is a constant. It has no variable. It is a constant. It is a number. So, with that in mind, with that said, when I said, hey, let's combine the like terms here, right? It's just kind of a clever way of saying it. What are my like terms? Well, my like terms are going to be my constants. Well, here is a constant, and this plus 2 is a constant. Okay, this constant, we don't know what it is, but it doesn't really matter. We're going to add 2 to it. It doesn't matter what the constant is. So what we can essentially do here is we can take this 2 out, and so my problem is going to just be x minus 2 natural log of x plus 2 and then plus some constant. All right, so hopefully that made sense. It doesn't matter what the constant is. Constant is comprised of just numbers, and the 2 at the end doesn't really, or well, I won't say that 2 at the end. In the end, this 2 doesn't particularly matter because it just gets lumped in with our constant here. Okay, so that does. Well, that's a very short section summary for everything that we just went over, but I guess that's it. All right, that does conclude today's lecture.